Thanks for that. Great. So as Abbie suggested, we'll cover a few things in this session today, but I first want to talk about some longitudinal measurement principles and really demonstrate some of the reasons why it can be really helpful to convert your research into latent variable models, and also some of the concepts involved. I'd then like to present two projects. Again, as Abbie said, if we don't get time to get through all of them, you have got copies of them. But the first one uses a latent difference score model to look at children's number line estimation and how that relates to later calculation problem solving. And the second study involves using an adaptation to the cross-lag panel model approach. And for that, we'll be looking at number transcoding and number fact fluency and how this relates to the sort of standardized tests that children get when they enter school. Okay, so first of all, in discussing longitudinal measurement, I really want to start talking about the sort of the what, the when, and the how, essentially. And I'll leave the more sort of why and who questions to Pam's presentation. But in terms of the, what are we measuring? To be clear, what we're going to be talking about today is less so the idea of multiple cross-sectional studies chained together like you might do in a cohort study, but instead looking at sort of latent constructs of things of interest to us that may be changing and developing that are a bit harder to get a handle on than a single measurement. So what I mean by that is if we consider something that might be more of the first case, you might look at something like the cost of a house versus relative income, and maybe you compare this across multiple generations and essentially using the same measure across time and getting a sense of that. But again, that doesn't work as well when we're talking about something more ephemeral like the development of a child's working memory span. In this case, it doesn't quite translate that you would think about it in this rather more simplistic view that essentially you have a capacity maybe that's just getting bigger and you have a sort of a bigger box that can hold on to more stuff. This is rather descriptive and doesn't get you very far. It sort of redescribes the tasks that you were providing to them. And instead, what we're more interested in is potentially the complexity of a more latent construct that we're interested in. So in an example here, we might consider something like the working memory span of a young child here. And if you sort of diagrammatically draw it out, you can imagine these are particular skills which we can measure with tasks. So maybe their ability to first attend to an object. So in the case of a young child, maybe this is the task of putting their toys away in different boxes. They can attend to an object that belongs to a certain box. They can encode that object and then store that in their sort of current working memory to decide what to do with it. But that's it. That's the end of the path there. That by the time they need to think about the next one, they're potentially forgetting what they're doing and they're not really showing working memory. So maybe they've got a capacity of one object. Whereas by the time we're getting to much older children, potentially with development, these connections are being made. All of a sudden the ribbon sort of ties up and now we've got something that looks a bit more like a working memory, which is these things repeating each other. But once you finish storing the current item, you can attend to other ones and keep the rule set in mind. So here we're talking about the nature of the latent thing we're interested in, the sort of ephemeral working memory part is this latent unobserved thing. But what we're measuring are these individual items. That's the what. Next, we want to consider the when. And in this case, what we're interested in is understanding that our construct, in this case, a toy example, which might fluctuate periodically, we don't know the nature of the change process that's undergoing our construct over time. And if we measure this at regular intervals, in this case, we might catch it at certain regular intervals that we can perfectly fit and perfectly predict the future outcome, but have no real idea of what the actual underlying change process is or the mechanisms involved. If we were, or if a different group maybe was to change how they measured this same process, they may get a very different idea with similar spacing and may get a very different set of predictions, but might closer represent the true change process. Now, again, this is a toy example, and we know that development and change is usually far messier in the real world. It's more often likely to be non-periodic, non-linear, and is also likely to undergo periods of critical periods where you might experience rapid change occurring, potentially non-linear, again, changes associated with other changes that are going on developmentally, and also recognizing that this may be a path that is followed by the majority of individuals, but there is going to be a huge degree of variability, and that variability is likely to scale over time. So understanding and also asking our question and coming up with a model of our question in terms of where do we think this belongs in the developmental scheme, but also when is best to be measuring this is important to be done at the point of asking your research questions. And the last important point to talk about, what I'll cover here is just the how section, which is how do we also account for the reality that if it's longitudinal data, it's likely to involve attrition of some kind. Again, I don't have a lot of time to talk about analysis options for how to deal with this, but just to sort of flag and raise that there are many options for dealing with this at the point of the analysis section, but more often than not, this should be key to planning and designing your study in the first case. So in the first instance, you may get fade out, where an individual eventually starts producing less and less data over time. Maybe this is due to motivation, or potentially something like asking someone to keep a journal, and they eventually produce less and less data over time. A dropout may occur. In this case, maybe a child moves school districts, and so you only have data for the first 2 time points and nothing after that point. The data may be missing completely at random. Missing at random to begin with, which in this case means that there may be something systematic about the way in which this missing data is occurring. So in the case of a child, maybe they are living between 2 households, or maybe this is someone with a regular appointment, like a dialysis, for instance, where they are missing regularly, and that may relate to something that you're interested in studying. Missing completely at random, this is more like the case where you may have a flu or an appointment, and so may miss completely unrelated to what you're measuring. And the last point is, again, we could talk a whole session about this, but longitudinal analyses planning for missingness, which is gaining sort of popularity, both in terms of making sure that you only collect as much as you need to collect, and again, using latent variables and using certain analyses to cover for this, but maybe capturing the necessary connections between variables, between enough people. And this is potentially a cheaper and more cost-effective, but also more ethical way of collecting data over time. So with these measurement principles in mind, I want to go back again to talk about the point of converting your theories into statistical models and predictions. So here are just, again, some examples of longitudinal models of change, which you may be familiar with or less so, but in the case of a basic statistical test, you may think of something like a repeated measures ANOVA, where you're interested in partitioning variance of repeated samples over time, and partitioning that between groups and variance within a group. These statistical tests are quite restrictive in the types of change that they allow and the distributions that they're based on. So in most cases, putting all of your data into a statistical test like this, it's very hard to see, based on those principles we've just talked about, whereabouts this change is occurring and what the nature of that change is. As we start to look at other models that can start to maybe tease apart this relationship, so in this case, the cross-lag model, we're interested in not only the predictions of the same variable over time, so how consistent is this variable over time, but also how well does that predict performance on other variables at different time points. If this is a time series data, then it really does rely on having the measurements at each time point. But again, we'll see later on that if we replace this actual measured variable with our latent variable, we can start to ask some more interesting questions. And then we're starting to get to more complex models which start to actually take into account both the starting point of someone, the intercept here, and the slope of change. And again, I'll leave the discussion for this to Pam's presentation, but here we can actually start to measure and model growth and change over time and allow for different functional forms to occur. Now, what I'll be using throughout the presentation is the classic model diagram defaults, which is we would use squares to denote the things we're actually measuring, and then circles to represent that, that latent construct that we're trying to measure, and maybe using multiple indicators of that. Okay, so to do that, two examples I want to show is from my own work, and the first of those looks here at number line performance. We know that children's classrooms are full of numerical materials, and some of those that are quite prevalent include number lines. And what we're interested in here is that children tend to have quite characteristic patterns of performance on these tasks. Early on, they don't tend to understand the fact that this line has the capacity to represent numerical entities as linearly spaced as they were in a number sequence, but instead, potentially they understand this as a spatial metaphor for magnitudes. That is, they overrepresent the distance between smaller numbers and they underrepresent distances between larger numbers. Those error signatures are very predictive of later performance in the sort of classical maths tasks we would think of. And in this case, the typical sort of verbal language math problem you might get in a test. You know, Riley goes to the market and buys 35 bananas and 18 pineapples. How much fruit did they buy? That sort of word question. So with that in mind, we're trying to see how these relationships exist over time. Now, this latent difference score model is a particular way of understanding change. And that model is actually including change as a predictor in the model. So if you think of what we would normally do, we've got, in this case, maybe the number line performance at time 1 and at time 2. What we would typically do maybe is run a t-test and see what that mean difference might be. And if there's a difference, we can infer that some sort of change has occurred. And as you may be aware, the t-test was first published by those working at the Guinness factory, but it has quite limited change that it allows for. And so what the latent difference score model does is, with a little bit of rearranging and a little bit of maths, is convert this difference. So rather than saying we've got the score at time 1, the score at time 2, we can then actually pull out that difference and actually make it a variable itself. So this is the change, this is the difference between the two scores. And what we're including here on this prediction here is how much does your score at time 1 tell you about what the change is likely to be across that time point. Again, we're not measuring change per se, we're measuring two different time points and there is a difference in change that has occurred. And typically we have to infer that statistically. And here we're saying we don't need to infer that statistically, we can measure it and have it as a variable in our model. Now, what do I mean by the relationship between the t-test? The t-test typically means you're assuming, again, this is the assumption, you're assuming that this beta value is 0, and that means that there is a perfect stability, that there's a difference in mean scores across time. So there's a change, they get better, but that is quite a regular stability of change. What's more likely is that there's going to be a change, but there's quite a degree of heterogeneity in that change. So this beta parameter can take that into account. Again, we don't need to measure actual variables, we can also measure our latent variables as well. So to do that, we looked at 4 time points and children were assessed roughly 12 months apart. And we used what I'm calling a partially overlapping longitudinal design. What I mean by that is at the first time point, we collected 0 to 100 number line performance, and also at the second time point. This way we could measure the change between those two time points. But at the second time point, we also know that children's performance on this 0 to 100 task is starting to reach ceiling, or they're getting quite accurate, and we want to know how precise they are. So we also want to measure what their performance is looking like on the next range. So this is trying to get to a point of measurement invariance. This is trying to get to an equivalence of the same latent construct, which is their understanding of spatial numerical relationships, but we're using two different indicators of it at different time points. Again, we can measure the change. And at the last time points, we can also measure the mental calculation performance. Again, we can actually quantify the changes occurred between these time points as model predictors, and then we can start to look at predicting those changes. So does change in one variable predict change in another at a future time point? Just to note that these are accumulated changes. We're taking into account the amount of changes previously occurred as well in all of our models. So what does that look like? Well, here's our three measures across our 4 time points. And again, we can see that this is a non-zero value for all tasks, which suggests that if we had used a t-test, we would be underestimating or overestimating the change. And instead, what we can do now is start to look at predictions and say, how well does change in one task predict performance or change in another task? We can also ask, how does change in one task predict future performance? And also, how well does prior performance predict the amount of change in future tasks? So instead of having a single test or a series of tests of t-tests, we've got an entire model here that is trying to at least capture the types of change we're seeing. What it also allows us to do is to look at mediation type questions. Typically, mediation questions are all collected at the same time point. And technically, it's very hard to actually infer anything about mediation without seeing it actually occur over time. So by doing this, what we found is that both the 0 to 100 and the 0 to 1,000 number line performance improves over time, perhaps suggesting that there's some sort of continuity of their representation over time. We also see that the 0 to 1,000 line performance was a mediator, but not the change in performance. What this suggests to us is perhaps that the amount of time that we're seeing between this time point is not enough for there to be a change in this task yet at this age. So like we saw with the original functional form description, potentially this change is occurring much faster at that age, and it maybe doesn't occur at the same speed for the 0 to 1,000 over the same amount of time. Second study, just to finish off with, is going to make use of the cross-lag panel model with a small recent update to it. And the question we're going to ask is, looking at school entry tests and how well do they predict future performance. Most children are given these tests upon entering school, and we wanted to know how well they were a standardized test at capturing some of this variability in 2 important tasks. The first one is number transcoding. So that is turning a written, translating between any form of representation of numbers. So in this case, we're looking at translating the written number symbol into a number word. So this is an example. Where someone has got a digit in front of them and the translation to the number word, there's been some sort of error there. And this is really showing how important it is to get this type of task correct for children. And the other performance we're interested in is number facts. So in this case, the daily example is something like needing to maybe find the number of objects you want to have in your diet per day and needing to add up the total number of fruit and vegetables to reach your recommended intake. So to give an example, to contextualize some of this cross-lagged panel model and the changes we're making to it, here's just an example using, imagine that you're using something like a touch typing test. So on this x-axis, you've got the speed at which a child can type, and then on the y-axis, you've got the number of errors they're making while doing this task. You may end up with something that looks something like this. And it's very tempting to start to infer something about speed accuracy trade-offs, that Potentially, as you get faster, maybe you're sort of catching the touch typers down here because they can make less errors as they're getting faster. But also imagine that this is actually the same person measured twice. And what you can see here is that there's two types of variability that we perhaps be interested in. The first is at the within child level. So that's saying that over time, children may differ in how the nature of this relationship exists. So this child here may have gotten slightly better, so maybe with some practice, whereas this child may have regressed to the mean. So there's some variability within children over time. There's also clearly some variability between children. Perhaps this child has access to a computer at home and maybe plays a lot of games, and so it's quite good. So the amount of change they can have is quite small, but they're already pretty good. Whereas this child may not have any access to a computer at all and may have gained a lot actually from doing the first test. So again, asking what is the relationship between speed accuracy doesn't really make a lot of sense without understanding this multi-level aspect. And so we're going to look here at number fact speed and the transcoding accuracy. Again, we've adopted a partially overlapping design. We've got 3 time points this time. And as you can see, we've increased the difficulty of this transcoding accuracy from 3 to 4 digits at the first time point to 4 to 5 and then 5 to 6. And number facts, the difficulty of the total sum, plus also the values in between increased. To quickly step you through the model, here's our cross-lag approach we saw before. So here we're only talking about the within child level. What we can see is that this is the prediction of the same task predicting itself over time. This is the prediction of the tasks across lagged. So how much does your transcoding performance at the second time point, how much of that can be explained by your number fact speed at the first time point and so on. What we can also then do is now take out that between child factor. And when we're talking about correlation, that's what we're interested in. We're interested in how children are different. And so this correlation is now differences between children, while also taking into account the differences within children. At the between child level, we know that there are some other measures that we've got that we can use to try and explain why they might be different. We know if we've collected these first maths and reading tests upon school entry, we've also collected some cognitive measures. So how fast can they count a collection of dots? How fast can they compare numbers? What their visual spatial working memory span is, and we also included their gender. Interestingly, for the number transcoding, more of a verbal task, did seem to be predicted by their math score and their reading scores upon entry. Whereas when we look at the number facts performance, only the maths test was a significant predictor, and their ability to count sets of objects was also, in small and large sets, was also predictive. But again, what you can see here is at the within child level, some of those predictions disappear because we've taken into account the differences between children. So just to sum up, what we really want to emphasize is that it's important to formalize some of these predictions that you've got ahead of time and sketch out what the types of models you might expect and what type of change you might expect so that you can design for that change to occur and being very careful about understanding the intervals between your predictions. In the first project I talked about, we saw that we can include change as an actual model parameter. When we do that, we can actually link change across tasks. The change only occurred at a single between 2 time points, so it's quite restrictive in the amount of change, but you can link those together across tasks. Again, that asks the question, what is actually the best spacing to be doing this? Should we test children more often, less often? And that will depend on what we're measuring. And we also saw that when accounting for differences between and within children, there are different predictions that were made at different levels. And we're hoping that by differentiating this, we can actually understand whether or not what we're seeing in a child's performance or behavior over time may be due to different levels of developmental change, whether that be a delay so that they will eventually catch up in that cross-lagged approach. Is it a difference that they just fundamentally look different, or is there a deficit they will never catch up? I want to, of course, thank Abbie and the rest of the organisers for inviting me, and my co-authors from the University of Melbourne, where the majority of this work was, all of this work was done, and where I am currently. And of course, it's invaluable that those involved in many-year, multi-centre data collection be involved for a long period of time. So, of course, we need to thank them. And I'll just end by showing some useful references that I've spoken about in the presentation. and yeah, hope for some other questions later.